Good afternoon, everyone. Just wanted to finish up, put together a screencast video to close out lecture slides on post-hoc comparisons. So we've gone through, talked about our contrasts and methods for calculating our contrasts, specific contrasts, confidence intervals around those contrasts, and then some effect sizes there. Again, remember that taking a look at small set of plan comparisons always your best approach. Okay, it's really easy to get deep in the weeds with looking at all possible comparisons with some of these ANOVA models. Your best bet is to have a good sense of what you would expect to see based on the existing literature, whatever your hypotheses are. If you just default to looking at all pairwise comparisons, you often end up looking at contrasts that aren't conceptually meaningful or interesting, and so if you're going through and going to responsibly look at all possible comparisons, also ends up in considerable reduction in power because you're basically incurring a penalty for each one of those tests that you take a look at. Okay, but sometimes post-hoc testing is going to be useful if you've got an experiment where it's purely exploratory. You're just kind of poking around with some looking at some preliminary data to try and generate some hypotheses for future work or things along those lines, or in cases where you have a lot of hypotheses, but you still want to, they're a priori, but you still want to correct for them. If you've got, say, 5 different hypotheses, that's probably too much to correct with a Bonferroni or a Scheffé, a Bonferroni or a Dunnett, and so you may want to impose some post-hoc test comparisons to prevent type 1 error and things along those lines. And we'll talk about in another lecture how to do that a little more specifically. But if you're going to use post-hoc comparisons, should know what they do, how they're being calculated, and things along those lines. So some post-hoc procedures that we're going to talk about. Fisher's LSD. Tukey's honestly significant difference and a couple variations on that. Tukey-Kramer and Games-Howell. Student Newman-Keuls, we actually probably won't use a whole lot with that, but we'll talk about kind of what it is. Scheffé's test and then Dunnett is the ones that we'll talk about in this screencast. Okay, so our first one is our Fisher's least significant difference. Okay, Fisher's LSD, all that you're getting with Fisher's LSD is a significant omnibus test. Okay, if you say that I'm going to use Fisher's LSD approach to comparing my pairwise tests, all you're saying that as long as I have a significant F test in the omnibus, as long as my ANOVA is significant, what I'm going to do is then I'm going to proceed through comparing all possible comparisons using that same T statistic, that derivation of that T statistic that we talked about previously with the planned comparison. So if you pull up here, you see a formula. So the T for the Fisher's least significant difference, we're going to have mean 1 minus 2 over the square root of the mean squared error from our ANOVA table over sample size 1 plus the mean squared error over the size of sample 2 or cell 2, and then we're going to compare this against a T critical with degrees of freedom error pulled from the ANOVA table. Okay, so basically Fisher's least significant difference has really no correction for multiple comparisons. We're saying that as long as we get that omnibus test that's significant, we're going to go through and we're going to compare things using a test statistic pulling from our mean squared error from our ANOVA table and evaluating those that test statistic against a critical T critical based on the degrees of freedom error from your ANOVA table. And so again, this is very powerful. Okay, Fisher's LSD is shown to be the most powerful among the post-hoc testing procedures. One, because you're basically establishing no penalty for multiple tests, and you're also evaluating against a T critical using the degrees of freedom error from your overall ANOVA table. And so if my overall ANOVA table has associated with degrees of freedom error of say 50, but each one of my 2 comparison groups only have 10 people in it, I'm still using that lower critical value to test my significance level there. So again, Fisher's LSD is shown to be very powerful, but criticized for not managing family-wise error and analyses with large number of multiple comparisons. You might be able to get away using Fisher's LSD if you've got a simple design, single factor, only 3 levels, but again, probably not something that you should be looking at if you, say, have violations of homogeneity of variance, or wildly unequal samples, or a large number of tests to compare. Because again, if we look at the formula for Fisher's LSD, it's just that same t-test that we had talked about with the planned comparison, pulling stuff from our ANOVA table. However, if you wanted to use that in an a priori way, what you could do is you could simply request Fisher's LSD from SPSS, and it's going to give you all those planned comparisons based on this formula, if you were to want to do that to look at your specific comparisons. So, but that's what we're talking about with Fisher's. Now, Tukey, in the studentized range condition statistic, Tukey is probably your most popular post-hoc test. Everybody loves a Tukey test. Okay. Once you guys understand where this is coming from, when we move into our factorial ANOVA, we'll start to use this a little more flexibly. Tukey and associated post-hoc procedures based on a different table of critical values. Okay. This table of critical values is called a studentized range statistic. All right. And our test statistic and our critical value is going to be set up a little bit different, very similar to a t-test, but a little bit different. So what we've got here with our test statistic, okay, so you're going to calculate your test statistic. Your Q is going to be the mean of one group minus the mean of another group over the square root of your MS squared error from your ANOVA table, and we're going to divide that by the number of individuals in each one of your cells. Okay, so in this formula here, X and L are given as the largest and smallest means in your set. Okay, so if you have 4 comparisons, 4 levels to your factor, the mean of L would be the largest mean, XS would be the mean of your smallest mean, taking that over the square root of your mean squared error and the smallest, the number of individuals in each one of your cells. Big thing to see here is that you've got this R. Okay, R is given as the total number of means in your set of comparisons. So again, if we have 4 levels to our factor, R would be 4. Okay, so but one of the things that makes this useful is we have a direct relationship between our T statistic and our Q statistic. Okay, so if our Q statistic, our test statistic, is mean 1 minus 2 over the square root of the mean squared error over n, our T statistic is mean 1 minus mean 2 over the square root of 2 times the mean squared error over n. And so if we go through and sort of manipulate this through the use of algebra, we get an equivalency between T and Q, where T is equal to your Q statistic over the square root of 2, or your Q statistic is equal to your T statistic times the square root of 2. Okay, so what we can do is we can move back and forth between a Q statistic and a T statistic in order to derive different critical values and then go through and use this flexibly. Again, we'll say a little bit more about this in our factorial ANOVA lectures. Okay, so primary difference between finding our critical T and our critical Q is that our critical Q values, same type of table, but when we're finding our critical values for our Q statistic, what we would do is we would find that value based on both the degrees of freedom and then also the number of means in your set, so R. Okay, so again, if we take a look at this insert here, we have just a section of our Tukey table. So this is for alpha equals 0.001. What we would do is we would take a look at our degrees of freedom error from our ANOVA table and say we had 10 degrees of freedom associated with our error term in our ANOVA table. So we would go down 10 degrees of freedom here, and let's say I have 4 levels to my factor. So I've got 4 different means that are being compared. I would find R equal to 4 because I have 4 means, 10 degrees of freedom, go down, and so my critical value for identifying a reliable difference between my largest and my smallest mean in my set, okay, would be, bring that cursor back, 5.77, okay. And so again, if we take a look at your full Tukey table here, you can see that we've got again, for 4 degrees or 4 means, this would be the difference between the largest and the smallest. So we would go down 4.33 being the critical value here. Okay, so note that if we go through and we take a look at, let's say we have a t-statistic with 20 degrees of freedom. Our critical value for a t-statistic with 20 degrees of freedom would be 2.086. Okay, so just a little over 2 would be our normal critical value for a t-statistic with 20 degrees of freedom. However, if we go down through this Tukey table, you'll see that at 20 degrees of freedom, if I'm just comparing 2 means, my critical value is 2.95. And if I have 3 means, the critical value would be 3.58, 3.96, so on and so forth. And so you see that with this Tukey statistic, what we have is we start to set a higher critical value for our comparisons relative to your just uncorrected t-statistic. Again, this idea being we need to set out a farther benchmark, a higher benchmark to reach, because we're going and we're calculating multiple, or we're doing multiple comparisons and things along those lines. Okay, so here's your Tukey table. There's a copy of this in Howell, obviously. Also, you can go online and find critical values to calculate your Tukey statistics, or find your critical Tukey values and things along those lines. Okay, so the main thing here is you don't get a specific p-value for your Tukey tests, post-hoc tests. What we would do, again, if we said we had 4 means that we were comparing with 20 degrees of freedom and the degrees of freedom error, we would just look to see any Q statistic that we would calculate. Want to have a Q statistic of 3.96 or less. If we are 2 groups were associated with a Q statistic of 3.96 or more, we would claim that that difference was statistically reliable at alpha less than 0.05 based on our Tukey test. Okay. So, how do we go through and we use Q? Okay. The idea behind Tukey and the studentized range statistic is that it's a true post-hoc test. What we're assuming is that you've gone through, you've ran your ANOVA with no idea or no a priori thoughts about what group is going to be different than what group. And so what we assume is that you've gone through, you've run your ANOVA, looked at all your means, and then said, oh, I wonder if these 2 means are different. Okay. Now, as we had talked about in class, this drastically alters the probability of computing type 1 or committing a type 1 error, because probably what's going to happen is you're going to notice the largest and the smallest values in the set, and you're going to say, oh, I wonder if these 2 things are different, right? But what you've done is you didn't come in thinking that those 2 groups might be different. You're kind of capitalizing on chance. And so what Tukey does is it goes through and it corrects for making those different types of comparisons. Okay, so let's say in this example that we have 8 people. We've got 5. Say we've got 5 levels to our factor. So we've got 5 different groups, 8 people in each group. Okay. Overall degrees of freedom error in our ANOVA table is 35, and let's say that our mean squared error in this in these analyses is 32.0. Okay, so remember our mean squared error. This is just our error variance. Mean squared is fancy ANOVA talk for variance. So our error variance is 32. We've got 35 degrees of freedom for associated with our error term. 8 people per cell, so we've got 40 people in this analysis overall. Here we've got our cell means. We've got group 1, 2, 3, 4, 5. What we would do if we were using Tukey is we would line these up, right, in order from smallest to largest. So we've got 4, 10, 11, 24, 29. Okay. What we would do then is we would determine the number of steps between our means to be compared. Okay, and this is going to be R. Okay, so if I wanted to compare to see whether there's a difference between x1 and x2, that would be two means that we're comparing, so that would be 2, so we would have R of 2 here. Okay. However, if I wanted to see whether or not mean 1 differed from mean 5, what I'm going to do is I'm going to have an R of 5 here because I've got 5 steps. 1, 2, 3, 4, 5. Okay. And so if you remember what we were looking at in that Q statistic, depending on whether or not we're looking at a difference of 2 steps or 5 steps, our critical Q value for our Tukey test is going to start to get larger. Okay. So what we would do, let's say, so I'm really interested because I just see a 4 and I see a 29, and I'm interested to beg, oh, I wonder if those two groups are different. What I would do is I would first calculate my test statistic. Okay, and so my test statistic in this case is going to be a Q with 5 steps, because 1, 2, 3, 4, 5. We're comparing our smallest to our largest, so we've got our most extreme groups here. We've got 29 minus 4 over the square root of our mean squared error, which is 32, divided by the number of people in each cell, which is going to be 8. Okay, so this gives us a test statistic of 12.5. All right. If we were to go through and take a look at our Tukey table, if we look at the Tukey table of alpha 0.05, we would find a critical Q value of 4.07 with 35 degrees of freedom and R5. And so we would go down through and we see that this value, our test statistic, exceeds our region set by our critical value here. And so that we would say that X1 and X5 are different, statistically different at alpha equal 0.05 using our based on our Tukey post-hoc testing. Okay, so again, simple, same type of thing we would do when setting up a t-test. It's just we're using a slightly different formula to calculate our Q statistic, and then also we're comparing our test statistic against a different critical value that we would get from our Tukey or our studentized range table, that Q table. Okay. All right. So again, procedure very similar to a t-test, just no specific p-value provided. We would just say that this contrast is statistically significant using a Tukey procedure at p less than 0.0 or p equal to alpha equal to 0.05. Okay. So no specific p-value for your Tukey tests. All right. Some alternative ways to use Q. Right. Now the way we had just gone over would be your typical example. You calculate your Q statistic and then compare with a critical value pulled from your table. But remember that Q and T are directly related, and so we can start to play around with this a little bit. So one thing we can do is we can determine a critical T value necessary to claim our statistical significance. So what we would do here, let's say that we have an ANOVA with 6 levels per factor. So we've got 6 total means, and let's say our degrees of freedom error is 47. Okay. If I were to go through my, and we probably wouldn't find this on the table, we'd have to get an online calculator to calculate this, but let's say that we go and we find that our, for a test with 47 degrees of freedom, our maximum Q critical for 6 total means. So at R equals 6, degrees of freedom 47, at alpha equal 0.05, our critical value for claiming significance is a Q of 4.23. Okay, so that's saying any test, any Q statistic that we calculate that exceeds 4.23 is going to be statistically reliable at Tukey alpha less than equal to 0.05. Okay, but let's say that we don't want to fool around with calculating Q statistics. Let's say that we just want to run some T statistics because we're more familiar with those. What we could do is we could take this Q statistic, right? This is our critical value, but because we know that T and Q have a direct relation, what we could do is we could take that critical Q and we can convert that into a critical T. Okay, and what we would do is we would take 4.23 and divide it by the square root of 2. Remember, we went back through a couple slides ago and took a look at equivalency between Q and T. If we take 4.23 divided by the square root of 2, we get a critical T value of 2.99. Okay, now if we were normally to take a look and look at what our critical value for a T statistic would be with 47 degrees of freedom, 47 degrees of freedom, our typical T critical value is 2.02, right? But here, because we've derived, so you've got this Tukey based on this critical value, so adjusting for multiple comparisons, instead of 2.02 being the value we need to find in our test statistic to claim statistical reliability, it's now 2.99. So this would be a T value, a critical T derived from our Tukey procedure up here. Okay, so what we could then do is then go through and take a look at any pairwise comparison using our basic independent sample t-test, right? We could just plug into SPSS, say I want to compare this mean and that mean, or that mean and that mean, or that mean and that mean. And any of those means, any of those test statistics that we found with a test statistic that exceeded 2.99, we would interpret that as statistically significant at alpha equal 0.05 based on our Tukey post-hoc testing procedures. Okay, so what you would do in this case is you could go through and you could say, all right, this is my critical value that I need any of my t-tests to come up with in order to claim that they're statistically significant based on our Tukey procedure. And then I can just go through and I can run whatever t-test that I want to, and ignoring the p-value. You wouldn't want to look at the p-value, but what you could do is you could go through and just look at the test statistic you got from that t-statistic in your output, and as long as it's larger than 2.99, we would say that that individual pairwise comparison would be statistically significant based on your Tukey correction for those tests. Okay, so basically what we're doing is we're hijacking Tukey, and we're taking that Tukey critical, the Q, translating it into a new critical T value, not the T that we would normally use for any pairwise test, but a new critical T that corrects for the multiple comparisons. And then what we can do is then we can just run the T-test that we're comfortable with, taking a look to see whether or not our actual test statistic exceeds our modified critical value based on our Q critical, and then make decisions on there whether or not we have evidence to reject the null hypotheses based on our adjusted t-test here. Okay. Another thing we can do if we wanted to, sort of using the same type of procedure, what we could do is we can determine the necessary difference in means that would be required in order to claim significance. Okay. So again, let's say that again we've got a Tukey critical is 4.23 for alpha equal 0.05. We're looking at a one-way ANOVA with 6 means, 47 degrees of freedom, and in this case, let's say our mean squared error is 32. Okay, what we could do is, if this is our formula for our Q statistic, mean 1 minus mean 2 over the square root of mean squared error over n, we can readjust this equation. We can refigure it to solve for the difference in means between the largest and the smallest. So we've got a difference score here equal to Q times the square root of the mean squared error over n. So in this case, if we go through and plug this in, we're looking at a mean difference equal to 4.23 is our critical Q value, times the square root of 32, which is our mean squared error, divided by 8, which is the number of people in each cell, equals 8.46. Okay, what we could do with this is then we could go through and instead of just running statistical tests, what we could go through among those 6 means within the my 6 levels of my factor, any 2 means that differ by amount greater than or equal to 8.46 units could be interpreted as statistically reliable at alpha equal 0.05 based on our Tukey procedure. Okay, so here we're changing. What we would be doing is deriving a new critical value for our t-test and then running t-test to see if our test statistic exceeded our new critical value. Here, what we can do is we can actually derive the minimum difference needed we would need to see between any two means in order to claim statistical significance. Okay, so here all we would do is we would take our Q value, our Q, translate this back, and then using this formula here, derive a different score. And any difference between two means that would exceed this, we could say was statistically reliable. And so again, a couple of different ways to go through, manipulate this Tukey statistic in the studentized range procedure in order to start to make corrections for the types of comparisons that we would want to make corrections on. Okay. So some different versions. So that's just the basic studentized range statistic. But there are a number of different things that we could do with this in order, depending on how we want to play around with stuff. Okay, and different versions of post hoc tests based on this studentized range statistic. First one we're going to talk about is Tukey's honestly significant difference, Tukey HSD. What Tukey HSD does is it takes a look at all pairwise comparisons and evaluates all pairwise comparisons at maximum values of QR. Okay, so in this situation, let's say we have a factor with 5 levels. All comparisons across all of those means would be treated as if they were 5 steps apart. So if we back up here, right, with the Tukey procedure, and there's student Newman-Keuls procedure will do this. If I wanted to test the difference between 4 and 10, I would test that at r equal 2. And if I wanted to look at the difference between 1 and 3, I would test this at a critical Q value with degrees of freedom 35 and r equal 3, because there's 3 differences here, right? So if I'm looking at values, means that are closer to one another, what happens is my R value is smaller, and so my Q critical is going to be a smaller value, right? If I'm looking at the difference between 4 and 29, that's going to be 5 steps, and so I would look at find a Q statistic, a Q critical with degrees of freedom 35 and R equal 5, and test this comparison using that R value. But what Tukey's HSD is doing is it's saying what we're going to do is we're going to compare all of these. Doesn't matter if I'm looking at 1 versus 2, 1 versus 3, 2 versus 4. We're going to evaluate all of these comparisons at the maximum R, which is going to be 5 in this case. So all comparisons, if we went through and we took a look at this, so our Q critical in this example, if you recall, was 4.07, right? We're going to compare any Q statistic between any of these all at 4.07. We're just going to have the same critical value for all comparisons in this, right? Which is different than some other tests that we're going to use, where you would use a different critical value depending on how far away these means were. So again, if we were looking at the difference between 1 and 3, we'd find a Q critical at alpha 0.05 degrees of freedom 35, but with R equal 3 if we were going to compare these two. Tukey's HSD compares all of these with the same R, the maximum R in there. Okay. So, Tukey's HSD for factor with 5 levels, all means would be treated as if they were 5 sets apart. So we'd set R to equal 5 for all of the critical values. So we'd say use the same critical value for all of those comparisons. What happens is we fix our family-wise error at alpha with Tukey's HSD, and what we're doing is we're correcting for all possible pairwise comparisons. Okay, just as a side note, we'll use this later on. A number of unique comparisons given as k times k minus 1 divided by 2. So with 5 factors, right? We've got 5 times 5 minus 1 is 4, so 5 times 4 is 20, divided by 2 is 10. So within a one-way ANOVA with 5 levels to your factor, so you've got 5 different means, there's 10 possible pairwise comparisons that we could be making. Okay, Tukey's HSD corrects for all of them. Basically, with Tukey's HSD, you're correcting for 10 post-hoc comparisons if you've got a factor with 5 levels. Okay, so what we would do is then we would contrast all of our pairwise contrasts against, if we're calculating Q statistic for each comparison, we'd calculate it against Q critical, the same Q critical for all of our comparisons. If we were running independent sample t-tests for each comparison, we compare all those with the t-critical. We would compute raw difference in means using degrees of freedom minimum based on that maximum Q critical that we had used in deriving that difference score there. Okay. Benefits of Tukey's HSD, one of our most popular tests. Good protection against type 1 error. If you see someone has used a Tukey test, they probably have used a Tukey's HSD, although you want to go through and make sure that that's actually correct. Okay. Drawbacks, though, if you're not interested in all pairwise comparisons, right? So you've got 5 levels of your factor, right? You've got 5 means. There's 10 possible pairwise comparisons that could be made, all right? But if you're only interested in actual 3 of those 10, if the other ones aren't meaningful theoretically or conceptually interesting, if you just go through and you run a Tukey's HSD, you're going to be correcting for 10, right? Instead of just the 3 that you're interested in looking at, right? And so what's going to happen is, because you're correcting for 10, the power of any one of those individual tests of the 3 tests that you're actually interested in are going to be much lower, because you're correcting for a lot of tests that you really don't care about. We have some considerations here in terms of power. You're also correcting for all pairwise comparisons, whether you report them or not. If you're running your Tukey HSD, you've gone through and you've taken a look at them, and probably what's going to happen is you're going to have some randos pop out, and then you're kind of stuck having to go through and account for those as well. So again, some of the drawbacks and limitations that we talk about post-hoc testing in general. Okay. So with Tukey's HSD, we're comparing all of our possible pairwise comparisons at the max level at the max critical value based on QR. Okay. Now, variations on Tukey-Kramer. This is just Tukey's HSD adjusted for unequal sample sizes. Again, formula is displayed here. Tukey-Kramer is the default in SPSS, right? Your classic Tukey test assumes equal people across sample, or equal number of people in each cell. That's obviously not the case in a lot of our research. Tukey-Kramer corrects for unequal samples. And so if you see a Tukey HSD in SPSS, what you're actually getting is Tukey-Kramer there, because it's adjusting for unequal samples. If you have equal samples, it just defaults to your standard Tukey, so no harm, no foul there. But know that if you just correct or request a Tukey's HSD, this is what you're getting. We also have a variation on Tukey's HSD called the Games-Howell. Games-Howell makes adjustments for unequal samples and unequal variances. Here, difference in all of our pairwise comparisons compared against a critical value WR instead of QR. Here is formula. You can go through, take a look, but basically what we're doing is we're taking making adjustments for individual cell variances, individual cell sizes, and so we're making an adjustment in terms of our statistic here, also making an adjustment on our degrees of freedom based on variances and sample sizes and things along those lines. This is similar to your Behrens-Fisher approach for your independent sample t-test. So when you're requesting your independent sample t and you've got the line down there that says unequal variant or equal variance is not assumed, this is basically your Tukey for unequal or equal variance is not assumed. Okay, so strongly recommend this in cases where you have unequal variance, unequal sample sizes, because we do have vulnerability in these tests to homogeneity variance when we have unequal samples and things like that. So if you have questions, you've got different sample sizes, and you've got questions where you think you might have discrepancy in your variances, this Games-Howell is probably where you're going to want to go if you're using some variation on Tukey. Okay, so again, Tukey-Kramer, default in SPSS, just adjusting for unequal sample sizes. Games-Howell, adjusting for unequal samples and unequal variances here. But basically the same idea conceptually is Tukey-HSD. Some other post-hoc procedures. Okay, you've got your Newman-Keuls test or your student Newman-Keuls test. This is a Tukey procedure in that we're using Q critical, but what we're doing here is we're setting our critical value, we're setting that R value as equal to the distance between each set of compared means, right? So again, if I'm looking at two adjacent means, my R for my critical value is going to be 2 there because there's only the 2 steps between those two means that are side by side, versus say I've got in the original example where I've got 5 means and I'm comparing the largest mean to the smallest mean, there would be 5 there. So depending on which specific test that comparison I'm making, we would have a different Q critical for each one of those based on how close those two means were together to each other in that set. So student Newman-Keuls is more powerful than the Tukey-HSD because again you're using a smaller critical value for means that are closer together, but less control over type 1 error. Okay, we're probably not going to talk a whole lot. We're not going to use student Newman-Keuls a lot here, but want to just present that so you know what that stuff's about. Scheffé test, also based on a Tukey procedure, but here instead of all pairwise comparisons, we're correcting for all possible comparisons. Okay, this is basically if you took all possible combinations of your pairwise tests and then also all possible contrasts. Scheffé is accounting for all of this. Extremely conservative and not recommended for looking at pairwise tests. Again, because you're controlling for all possible comparisons, not just all pairwise comparisons, and so you're going to be correcting for a little bunch of tests that you're actually not making. So Scheffé, extremely conservative, but not recommended for your standard pairwise testing. Okay. And then finally, you've got Dunnett's test. Dunnett. Here what we're doing is we're comparing some control group or some reference group with every other treatment mean. Okay, critical values are based on a different table. So let's say in that example where we've got an ANOVA table or an one-way ANOVA with 5 different means in it, right? We've got 5 different groups. What we would do in Dunnett's is we would compare. We'd have some reference group, some control group, and basically we get control versus group 2, control versus group 3, control versus group 4, control versus group 5. Okay, so very nice, an excellent test if the nature of your question is such that you're not really interested in differences across groups 2, 3, 4, and 5. You're just interested in the extent to which these 3 or these 4 groups differ from your control. Dunnett's test would be the one for you to take a look at. So it's a good test, but much less flexible because basically all you're getting with Dunnett's is a comparison with a reference group. Okay. Which test is best? All right. Depends. Right. Depends on your hypotheses, your design, your aims, things along those lines. Okay. Again, if we've planned our test in advance, we're only interested in a few comparisons. Again, this is where I would strongly encourage you to go. Here we can use just our independent samples t-test, correction for Bonferroni, Dunn-Siddick correction. If you've got a small set of comparisons, if you've got relatively equal samples, haven't violated homogeneity of variance anywhere, you can even start to substitute your mean squared error from your ANOVA table and compare against a critical value using the degrees of freedom error from your ANOVA table. If not, if you've got unequal cell sizes or violations, probably just run your independent sample test. But in general, your planned comparisons are going to be best. Okay. Tests are planned in advance. Interested in complex comparisons, this is where you're looking at linear contrasts. Okay. Again, if you're interested in the extent to which groups 2 and 3 differ from group 1, that's where you're going to want to get into some of your contrasts and things along those lines. But if you've got a large set of exploratory post-hoc tests, Tukey, those variants, generally going to be your best approach. Okay. So, want to go through and quickly take you through the handout, the post-hoc handout that we had given in class. We didn't get a chance to get at this. This is your one-way ANOVA with your post-hoc test. So this is the data set you would pull up if you want to play around with this on your own. And you will want to do this just so you can go through and see. I'll have some stuff on this demo, but you want to go back through and take a look here. With this set, what we've got is we've got a group of people who have experienced chronic pain. Okay, these are people who have chronic pain that has been untreated, causing some sort of impairment in their day-to-day functioning over the course of, say, 3 months or more. And what we're interested in here is whether we see differences in trait-level anxiety across a few of these different profiles. So profile 1 is an adaptive coper. All right, these are people who have chronic pain, but they get around pretty well, some limitations, but little psychological distress, and they're able to manage it. We would say these are people who are doing pretty well with managing their pain. Group 2, an interpersonally distressed group. Okay, these are people who rely on other people for help, maybe excessively so. These are people who have regular complaints to their friends, family about their chronic pain, rely on friends, family to help them manage their pain, but as you can imagine, can start to tax interpersonal relations with this interpersonally distressed group. The dysfunctional group, this is a group that is just relatively low functioning in terms of their pain, a lot of avoidance, not doing so well. Hybrid is a combination of these first 3 groups, and then other is the catch-all of people who don't fall into this group. Okay, so basically we've got 3 or 5 different types of coping profiles, right? So we've classified people as adaptive, interpersonally distressed, dysfunctional, hybrid, or other in terms of their pain coping. And what we're interested in is if we see differences in trait level anxiety across these 5 groups. Okay? So as you're looking at this, make sure to pull up your one-way ANOVA handout as we're stepping through this stuff. Okay? So what we're going to do, here's our data set. Okay, so we've got our participant number, our trait anxiety, and a profile level. Looks like we have missing value here, several missing values. That's fine, it just won't include those people. We can go through and delete. Well, now I'm worried that I screwed something up here. Just want to make sure that my numbers don't deviate from yours. Let's see here. That one. No. Okay. Okay, here we are. We're back with our original data set here. Okay, I'm actually going to go through and save this as a scrap set, just so if I screw it up, I won't ruin the actual data here. Okay, so we'll go through, sort this. We've got 4 cases that have missing trait anxiety, so we're going to clear that out. And so we're left with just 106 individuals. Okay, so what we're going to do, again, interested in seeing whether or not these groups, the different pain profiles different in terms of their trait level anxiety. So what we're going to do is we're going to go to Analyze, down to Compare Means, to One-Way ANOVA. Okay. We're going to select Trait Anxiety as our dependent outcome, and Profile as our IV. So this is our factor. We're going to go to Post-hoc, and we're going to choose least significant difference. Okay. SNK, student Newman-Keuls, is on your handout, but we're going to ignore that for right now, so don't worry about that. And in the assignment, don't worry about your student Newman-Keuls. You can ignore that. Tukey, this is actually your Tukey-Kramer, but this is your Tukey-HSD here. What else do we want? We're going to request Games-Howell. Okay. Again, this is looking at different samples and different variances. we're going to request Dunnett, right? This is where we're comparing all of our groups to some control category. Here, if we pull it up, right, in this case, our adaptive copers are probably our best bet. So we're going to set our control category to be our first. Okay, so basically what this does is this is going to look at levels of trade anxiety comparing all other groups against our adaptive copers. Okay, so we've got 1, 2, 3, 4. And then Scheffé, even though we won't ever use that because it's far too conservative, but we'll go through and take a look and see what's going on there. So that's 5. I think that gets us all. Significance level, we'll keep it at 0.05, but you could adjust it there if you wanted. We're going to hit continue. Okay, going to go to options. We'll ask for descriptives, homogeneity of variance, our Welch's test, right, as we had before, and then we're going to hit continue there. We'll paste it. Okay, so this is what your syntax file will look like. All right, so we're just going to highlight that and run it. Okay, so taking a look from the very start, we want to go through down and take a look at my descriptives first, right? Notice that I've got pretty evenly matched samples except for this hybrid. Okay, so and we've got a clear discrepancy in sample size. If it was 23, 23, 25, and 27, that's pretty close. I would say that they're clearly not all the same, but they're reasonably similar, right? But here we've got this hybrid group that's very low, and so we have some concern about unequal samples here. Going down through, looking at our means, we see, as we might expect, our adaptive copers are demonstrating much lower levels of trade anxiety than some of our other groups. Okay. In terms of our standard deviations, remember our assumption is our equivalence of variance, but sort of the difference between 8 and 14, that could start to become problematic, right? So might have some concerns on whether or not we have equal variances here. Then we have our confidence intervals around our means and our minimum and maximum. So just based on this descriptive table, we know we've got some issues with equal sample sizes and maybe some differences in terms of variability around average score within each group in terms of state anxiety. If we go down to our Levine's test, see our Levine's test is marginal. It's right on the edge, right? So technically we don't have sufficient evidence to claim differences in our variances across our groups, but it's still something on my radar. So something I want to think about a little bit. Sort of a borderline case here. We look down at our ANOVA table. We see a significant, clear significance in terms of our omnibus test. We could go through, calculate an eta squared, omega squared, get us an effect size for that omnibus test. What's going to be relevant if we were to go through and calculate some of this stuff by hand. Notice that our mean squared error here, our within groups error is 135.8. We could take the square root of that to get sort of our pooled standard deviation. But again, we've got some concerns with differences in sample sizes, and so not 100% confident that that's a good estimate of the variability across all of our groups. Degrees of freedom error, so we got 101 degrees of freedom error based on our table here. That would go into, in a normal case, would go into determining what our degrees of freedom would be for our critical value, 101 found here. This is our Welch's test, our robust test of equality of means. Even if we decide that yes, that suggests that we should assume unequal means, our omnibus test is still going to be statistically significant, so no concerns there. All right. Now we're going to drop down into our post-hoc tests. Okay. This isn't going to be on the handout I gave you just because it's a really long table, but you can go through and pull this up and take a look on your own. So our first post-hoc test that we have here is our Tukey-HSD. Okay, this is our Tukey-Kramer, but essentially what we've got is looking at this, so our comparison group in sort of this section of the table is our adaptive coper, and we're looking at our adaptive copers versus our interpersonally distressed, our dysfunctional, our hybrid, and then our other groups. Okay, we see the mean difference. This is the value of our contrast. This is the mean, or the difference in the two group means. We've got our standard error. We've got our significance values, and then it's giving us an upper and lower bound confidence interval for the mean difference. This is a value of our contrast here. So this is nice. It's giving a lot of good information. And so again, this is your Tukey HSD. So what you're doing here is you're looking at the statistical significance of each one of these groups, adjusting for a total of R equal 5, all 5 means. So all of these tests are being compared at the maximum R level on Tukey. Okay, so here we can see that our adaptive copers are scoring lower on trait anxiety than our interpersonally distressed and our dysfunctional groups after sort of controlling for multiple comparisons with this Tukey procedure. Okay, we're not seeing a difference between our hybrid and our other groups and our adaptive copers. Okay, so again, statistically significant differences here and here. Confidence intervals around this, but then again, if you look at your confidence intervals here, we see that these include 0. So again, just another way of looking and saying, yep, it doesn't look like these are statistically reliable after making adjustments for Tukey. Okay, here we go down and we're looking at our interpersonally distressed versus our adaptive copers, but we've already sort of looked at that up here, right? This is just how this table is set up. So we see a difference between our adaptive copers and interpersonally distressed. We already knew that. Interpersonally distressed don't look like they're different from dysfunctional, hybrid, or other groups. Here, our dysfunctional, again, different than our adaptive copers, but we already knew that because we got that here. But if we go down the list, we see a difference between our dysfunctional group and our other group. Okay, this is one test that hadn't been gotten up here. So dysfunctional and other, with our other group scoring higher or lower levels of trait anxiety than our dysfunctional group. And we can go back up here and say dysfunctional, higher levels of trait anxiety than our other group. Okay. And then if we go down through and take a look, we're not seeing any other differences that have been picked up to this point. So our Tukey HSD procedure, and this is our Tukey-Kramer, right? Adjusting for unequal samples, we're getting finding that our adaptive coping people are showing lower levels of trait anxiety than our distressed and our dysfunctional group, and we also see that our other group is scoring lower levels of trait anxiety than our dysfunctional group. So we've got 3 statistically reliable differences based on Tukey HSD. Okay. If we go down to our Scheffé, though, remember that Scheffé is controlling for all possible comparisons. This is controlling for all pairwise comparisons. So essentially, this is controlling for all 10 unique comparisons here. Scheffé is controlling for all possible comparisons. And so again, if you go through and you take a look, this adaptive coper versus this interpersonally distressed, that was statistically reliable when we're using our Tukey-Kramer, it's no longer coming up as statistically reliable using Scheffé, okay? Just demonstrating that this is a more conservative test than Tukey HSD. Also, our adaptive versus our dysfunctional was a statistically significant P equal 0.001. That's still statistically reliable, but you can see the effects of a more conservative test. And if we go down through and we take a look, no other comparisons that are registering as statistically reliable based on your Scheffé test, again, because it's just putting a more stringent threshold on your comparisons. Okay. Fisher's LSD, remember that this is no corrections, right? This is just your basic t-test that we had gone through when we were talking about our contrast and pairwise comparisons. So all we would need to do is go through and see we have a significant f-test, and then we can just go through and compare without any restrictions after that. And so we see, again, our adaptive coper and our interpersonally distressed are different. Our adaptive coper and our dysfunctional are significant. But again, these p-values are lower than with the Tukey-Kramer. We also see a marginal effect here between adaptive coper and hybrid. Again, looking at the sort of basically no restrictions with the Tukey-LSD. And again, so these are coming up, our dysfunctional and our other, again, registering as significant. So similar effects to our Tukey-Kramer, but looking at these p-values, seeing less conservative tests with the Fisher's LSD. And then finally, or not finally, we got a couple more, our Games-Howell. Remember, Games-Howell is correcting for unequal variances and unequal samples. And so here we say that this adaptive coper and this interpersonally distressed is just right on the edge, but technically no longer statistically significant after we've adjusted for unequal samples and unequal variances. We still have a difference between our adaptive and our dysfunctional groups, and a dysfunctional in our other groups, right? But this is going to jump around, and it's difficult to tell. It's not necessarily more conservative or less conservative. It's just taking into account differences in means and differences in standard, or differences in cell sizes, differences in samples, sample variances and sample or cell sizes. In this case, I would probably be looking at Games-Howell, given sort of a pretty significant discrepancy in my cell sizes and possible differences in my variances. Okay, so in this case, I would probably be looking at Games-Howell just to play it safe. Our final test here is our Dunnett's. Again, remember, Dunnett's is just we're choosing a control group. Here are adaptive copers, and we're comparing all of our other groups against our control group. And here we see that we see a difference between adaptive and interpersonally distressed, difference between adaptive and dysfunctional, and then our adaptive versus hybrid, adaptive versus other aren't changing around a whole lot. Okay, so a nice test if you just want to compare all your other groups, go to a control group. Otherwise, may not be super helpful. Okay, and so down here we have homogeneous subsets. You can ignore that. Don't worry about it. I'm not going to hold you accountable for that. This is just sort of a different way of displaying some of this stuff. Worry about this stuff in this table. Okay, so overall, we're seeing some differences across our comparisons. Now, at the end of the day, we're getting some similar outcomes, but you can start to see how some of these tests are more conservative than others. So wanting, again, like everything else, to go through, take a look, ask what your research question is, what are your hypotheses, if you have any, what means and comparisons do I want to make, and then looking at sort of technical aspects of your analyses. Do I have relatively equal people in my samples? Do I have evidence of fairly similar variances? Things along those lines. For this specific example, you could go with your Tukey-Kramer here, but I'd probably want to go through and probably use Games-Howell, given that the equal homogeneity of variance assumption is sort of on questionable grounds. Fisher's LSD, that's too liberal, that's not going to work. Scheffé, that's too conservative, not going to want to do that. So it's going to come down to the Tukey-HSD, the Tukey-Kramer, or the Games-Howell, depending on what argument you want to make on whether or not you're taking this Levine's test literally, or thinking, well, I might have some problems there. Okay, so this should get you squared away with the post-hoc test, all the things that you would need for problem set 7. But again, let me know if you have any questions. Go through, take a look, and if anything comes up, go ahead and let me know. All right, thanks everybody.